All right, cool. So the reading for this week was 2-3. So chapter 2, section 3 on generalized elements. So he considers initial objects, arrows into initial objects and arrows out of terminal objects. So normally, we think of so an initial object is an object that has an arrow into every other object, but some objects have arrows into the initial objects, and those can be interesting. So he says that, those are special interests. So in set or in Hask, only terminal objects have arrows to from other terminal objects. So if an object has an arrow from a terminal object, that thing is unit, the one object set. And only initial ones have arrows into initial objects. So if a set has arrows into initial objects, then that thing is the empty set. And in monoids and groups, every object is both initial and terminal since there's only one object, right? Okay, so then he goes on to give an example of some interesting categories that have objects with arrows into initial ones and out of terminal ones. So for instance, he gives the category of Boolean algebras. So let's see. So we know the initial Boolean algebra 2. So that's really familiar to us as programmers. It's the set with two objects in it, or two elements. We normally think of them as 0 and 1, or true and false. False and true, 0 and 1. And other Boolean algebras all have arrows out of this one, since it's the initial one. That is, every other Boolean algebra has a true and a false object that preserves the structure of the Boolean algebra. Okay, but every one of them also has a map into the initial object, and those are called ultrafilters of that Boolean algebra. So this map from the Boolean algebra B to 2 essentially splits that Boolean algebra in half. So we have a set. A filter then is a subset of the Boolean algebra B, where either an element in B is in that filter or it isn't, and it's in the filter if this P map returns true, and it's not in the filter if it returns false. Right? So maybe we should go over what a Boolean algebra is. Did you guys read that bit? So let's see. All right, so a Boolean algebra BA is a poset, B is a poset B, right? With special elements 0 and 1, which are false and true, respectively. There is and an or. And an or, which are the usual sort of binary operations, right? And then a unary operation not. Not.
What makes a binary or Boolean algebra a poset? Is that the mappings from 0 to 1 to other things?
What makes it a poset is that it's required to satisfy certain conditions, and those conditions are on page 34. So it's an ordered thing with 0 at the bottom and 1 at the top, and then everything is in between. So you can think of a Boolean algebra as a power set. So he talks about that on that same page 34. He says there's an equivalent fully equational characterization not involving ordering, where a typical example of a Boolean algebra is the power set of all the subset of a set, ordered by inclusion, right? So then B is actually the power set of X for some other set X, so it's a set of all the subsets of X. And then the element 0 is the empty set. So we say 0 is empty. 1 is the whole set. Right? And then and is set intersection, or is set union, not is complement. Right? We actually went over this last time, I think. Yeah, here it is. A Boolean algebra can be characterized as a power set, P of X. So this is from last session. So all the subsets of some X ordered by inclusion. 0 is the empty subset, 1 is the whole set, or is set union, and is intersection, not A, is X minus A. So it's the complement of A. So it's all the elements of X that are not in A. The initial such algebra is the familiar two-element set bool, and the terminal one is the one-element set, where the true and the false, or the 0 and the 1, are both the same. And we can consider this a poset because, you know, the ordering is set, so the subset relationship. Okay, so now we know what a Boolean algebra is. We can go back to this here, the category of Boolean algebras. Okay, so an alter filter on a Boolean algebra is a map into the initial Boolean algebra. So basically, for every element of B, we can assign it either 0 or 1, right? So it's either in the filter or it's not in the filter. And it's actually stronger than that, and which we'll see. So it's a non-empty subset of the set B, such that if A is in F, an element of B, right? If that is in F, then every element larger than or equal to A is also in F. So we can say if A is in F, then every superset of A is in F as well, if we think of it as power sets. So if A is in the filter, then A and up are in the filter. If A and B are both in the filter, then A and B, the intersection of A and B, is also in the filter. Make sense? It's a little bit abstract at the moment, but we can see how that works. So a filter, U, so now we know what a filter is. Then a filter is an alter filter or a maximal filter if the only strictly larger filter is the whole set, is all of B. Then every filter is an alter filter precisely when, for every element B in the set B, either B is in the filter or not B is in the filter, and not both. So it's even stronger than this filter condition so you can see that if this map P gives true or false for any given element of B, then it's either in the filter or it's not. But it actually says something even stronger, which is that if B is not in the filter, then not B is in the filter. Does that make sense? So the complement of B is in the filter if B isn't. So this map from B to Boolean, or B to 2, splits the elements of the set into those B that are in the filter and those not B that are in the filter. Okay, Yeah, so here I made a note that it's not just those B and F and those B not in F, but it's more strongly for every B B is not in F, then not B is in F. Okay, so we can prove that P generates an alter filter. So all we need to do is to show that P generates some filter, which is strictly smaller than the whole set B, such that no filter exists between F and all of B. So since we know that P is a homomorphism among Boolean algebras, we know that it preserves some relationships. We know that it preserves the 0 and the 1. We know that it preserves the subset or the ordering, right? We know that it preserves intersections, unions, and complements. So therefore, we also know it's a filter, because this number 1 here is a homomorphism law. So if A is less than B in the original set, then P of A is less than P of B. That is, if A is in F, that is P of A is equal to 1, then so is B. Because if P of A is 1 and P of A is less than or equal to P of B, then P of B is definitely not 0, because 0 is is not greater than 1, right? So this is the first condition, that if A is in the filter, then if B is larger, then B is also in the filter. Make sense? So since this is a homomorphism, it preserves this relationship, so that if we assign A to 1, that is, it's in the filter, then we necessarily must assign B to 1 as well, because this less than or equal to relationship has to hold. Okay. The second condition was that if P of A, if A and B are both in the set, that is, if P of A and P of B, then also P, A, and B, right? Since this is a homomorphism, if A is in the set and B is in the set, that is, if both of these are 1, then P of the intersection is also necessarily 1, and vice versa. If this is 0, then this is also 0. Make sense? So the simple fact that it's a homomorphism proves that it's an alter filter, right? So P of the empty set is 0. P of the whole set is 1. Since it's a homomorphism, it maintains this relationship. So the empty set is never in the filter, and the whole set is always in the filter. And then for any given element, either that element is in the filter, or the complement of that element is in the filter. But since it's a homomorphism, then to say either B is in the filter or B is not in the filter, right? So not P of B. So P of B is either 1 or P of B is 0, right? So since it's a homomorphism, then P of B being 0 means that P of not B must be 1. So for example, if B is the set ABC, then either the element B or the single element set B is in the filter, or the complement, the 2-element set AC, is in the filter, but not both. In fact, if B, the single element set B is in the filter, then all the sets containing B are also in the filter by 1. Right? So all supersets of that set, the single element set B, are also in the filter. Right? We can also say that if the single element set B is in the filter, then it's a contradiction that, for example, the single element set A is in the filter. Because then the intersection of A and B, or these two sets, single element sets, would also be in the filter by the homomorphism law, and that intersection is empty. And so that would contradict with the homomorphism law. So we know that the empty set is not an F. Therefore, P is true for the for the single element set containing B for exactly one element and no others. So no other one element set is in the filter, and the empty set certainly isn't. So there is no strictly larger filter of the power set. Therefore, P constructs an ultrafilter. Do you follow that?
I think so. My bigger question around is what's the logic of or this language of like being closed under and over that's used in the book and some of the terminology that's used there.
Oh, can you point me to the...
So at the beginning of 2.3 and like the third paragraph, it's like a filter in Boolean algebra is a non-empty set. F is a subset of B that is closed upward and under. And then all this makes sense, but like the terminology that gets used is sort of...
Oh, right. So he's actually defining that. That's actually something that can be difficult with like mathematical texts, is that sometimes you'll see a term you don't recognize and don't realize that term is actually being defined, like in line, right? So he's saying it's closed and upward under meets, and then after the colon, he says what that means, right?
Okay.
So he's saying if it's closed upward, that means that if A is in the filter and A is less than B, that implies that B is also in the filter. So it's closed upward in the sense that for every element A, if it's in the filter, then everything upward of A is also in the filter. And then it's closed under meets in the sense that if if two elements are both in the filter, then their meet is also in the filter, right?
Okay.
It's just like a set being closed under some operation. So for example, the integers are closed under addition, right? So the addition of any two integers is also, the sum of two integers is also an integer.
So in line 51, there's one such ultrafilter for every element of B. If I have, say, a subset of B, so A and B, or lowercase a and B of uppercase B, then, and they're not in the filter, then I could have, say, an ultrafilter for that unified subset as well.
I'm sorry, point to me again. What are you reading?
So line 51, you say there's one such ultrafilter for every element B?
Yes.
If I have the superset, or not the superset, the power set of B, for every element in the power set, there's also an ultrafilter for that?
Yeah. Then you consider the Boolean algebra being the power set of the power set.
Okay.
Yeah. But if you take a look at, and actually I'll share with you a Chrome window. If you go to ultrafilter on Wikipedia, there's a really cool diagram, which I'll just go to for the video's sake. I'm going to stop share and then reshare. Okay. So now you should see that. So in this diagram, you can see that so everything that's shaded in green and yellow is an ultrafilter above 1. So for every one of these elements, 1, 2, 3, and 4, there's an ultrafilter of this power set. This is the power set of the set 1, 2, 3, 4. So each one of these bubbles is a subset of the power set. Sorry, is an element of the power set. Then you can take each one of these elements, 1, 2, 3, and 4, in the bottom rung, and you can select one of them. And an alter filter then will contain everything above it. So you can see that, if we select 1, then every superset of that 1 will be in the alter filter. And then you can also see that, so 1, 2, and 1, 3 are both in the alter filter. Then the intersection of them is also necessarily in it. So 1 is also in it. So this relationship works both upwards and downwards in that sense. Right, so if we added one of these other bubbles to our filter, then we'd have a contradiction. Like if we added 2, 3, then we'd necessarily have to have the intersection of 1, 3, and 2, 3. So we'd have to have 3, and we'd have to have the intersection of 1 and 3, which is the empty set. And that contradicts with the homomorphism law that the empty set is not in the filter, because P of the empty set should be 0. Right? So it creates this really sort of interesting structure in the lattice of Boolean algebras. Right, so we can, and this is an example of a generalized element. So 1, 2, 3, and 4 are not only elements of the set 1, 2, 3, 4, they are sort of generalized elements in the category the Boolean algebra considered as category.
So I'm looking at the Wikipedia page as well, and it mentions the term lattice, the power set lattice. I've heard the data science engineers mention that term a lot. Is that basically what we're looking at?
I don't know. I wish we had one of the data science people here to tell us. We'll have to maybe ask around. Okay.
I know John might know a thing or two about it, and I may need to pick his brain about it as well.
Yeah. Okay. So then what was after alter filters? Oh yeah, so he talks about truth tables. So an alter filter actually being related to truth tables. I'm going to share that again. So yeah, we can note that we can model an alter filter as a functor from a Boolean algebra to the category 2. Which looks like this. There's 2 objects, 0 and 1, and there's 1 arrow between them. And of course, 0 and 1 both have identity arrows. So there's an initial object 0, a terminal object 1, and this category models a truth table for material implication. So the arrows in 2 are exactly the true rows in the truth table for material implication. So 0 implies 0, 0 implies 1, and 1 implies 1. So then it goes into practical applications. So yeah, I guess, well, this is just something I was trying to think up, like what are some practical applications of alter filters? Okay, so an alter filter of a Boolean algebra of strings of binary digits, which we all recognize from computer science. We work with strings of bits all the time. So an alter filter of a string of bits will contain 1 in a particular position. So it'll be the set of all the strings with 1 in a particular position, and only those strings with 1 in that position. So it's sort of like a mask, right? Where we say, like, I want this bit to be set, and the filter will match everything with that bit is set.
Is that then a church encoding composed of logic gates that basically encodes that value?
I'm not sure what you mean by church encoding in this case.
So if you had a function, which is in this case the mapping from the Boolean algebra to the 2 set, which was basically composed or comprised of a bunch of and or gates and not gates and things like that, then it would encode that a particular value has a 1 in a particular position. So it could be a church encoding of, say, that value comprised of logic gates.
Yeah, it could certainly be I mean, there's certainly a correspondence between, you know, filters like that and their implementation in logic gates.
Because then it might be an interesting application of like chip design for a compiler for chip designs.
Yeah. Okay, an ultrafilter of a relational database. So the set of all query results that contain a particular row, and only the results that contain that particular row. So you can say, like I have, because we can consider relational algebra as a kind of Boolean algebra, and then we can take an ultrafilter of the database. So we select a particular row, and the filter will match every query result that contains that particular row. Ultrafilter in type theory with subtypes is final. So I thought that was kind of interesting. So a type with no subtypes is an ultrafilter in Scala.
Is that a final class in Java?
Yeah.
Okay.
Yeah. So its only its only subset is the empty set. So the only strictly larger the only strictly larger type no, sorry. The only strictly larger filter so is all the types, all the Scala types. Right. So it's like it's a bottom rung type. So sort of a generalized elements of the Scala type system are the final or the primitive types. Okay, so then he goes into prime ideals, and this is where things get a little bit mathy. And actually, I got myself to a point here where I just needed to quit, and I couldn't actually figure out how to prove this, but I had sort of a sketch. So to understand this requires a bit of ring theory. But we can understand a lot of this just in terms of category theory. So he makes an offhand comment at the bottom of page. Where is it? Yeah, bottom of page 35. He makes an offhand comment that ring homomorphisms from A to Z into the initial ring Z, which is the set of integers, plays an analogous and equally important role in algebraic geometry. They correspond to so-called prime ideals, which are ring theoretic generalizations of ultrafilters. The statement is a little bit confusing because when he says they correspond to so-called prime ideals, this is not a one-to-one correspondence. So they don't correspond to the prime ideals. There are prime ideals that do not correspond to ring homomorphisms. But we can say that there's a ring homomorphism into the initial ring of integers for any given ring R. Then that is a prime ideal. Okay, so what is that? So first, a reminder of what a ring is. So a ring has an addition, which is associative and commutative, and has an identity element, 0. So it's a commutative monoid in plus. It has a multiplication, which is also associative and has an element A. So it's a monoid in the multiplication. And it has a negation. So it has an inverse for each element, which is preserved by addition. So so A plus negative A is 0. And negative A plus A is 0. Right? Star in one form a monoid, and plus and 0 form a commutative monoid. And then star is distributive with regard to plus. So multiplication, distributes over addition in the usual way. Then a prime ideal of a ring is a subset P of the ring, which is either the empty set, it's the one element set containing just the 0 of the ring, or it has the following properties. And actually some classifications of prime ideals disallow the 0. So actually texts do not agree on this. Okay, so what they do agree on is that it has the following properties if 0 is not considered. If if the multiplication of A and B is in the ideal, then either A is in the ideal or B is in the ideal. And the other condition is that the prime ideal P is not the whole ring R. So it's strictly a subset of R. So for example, the set of even numbers is a prime ideal for the integers. So if we take R over R, where R equals 2, so it's actually the slice category of the ring R. So we take the slice over 2. Then we can see that if A and B is in the prime ideal, then one of these is going to be a multiple of 2. Either A or B is going to be a multiple of 2. So basically, if AB is a multiple of 2, then A or B is a multiple of 2. Make sense? Where P is now the set of even numbers. So P is the multiples of 2. Yes? Okay, so in general, the prime ideals of the integers are such that R is prime and has the following properties. Every element of P is a multiple of the prime, the given prime R, and every multiple of the prime R is an element of the prime ideal.
Does that mean there's a homomorphism from, say, the prime ideal of a set of integers to the number times multiple each element of that prime ideal set is to the original integers itself?
I did not follow that. I'm sorry.
So if you have, say, a prime ideal where R is 2, so you have all the even numbers of a bunch of integers, and then you take each element that's in the prime ideal, which is a multiple of 2, and take the number of times it's a multiple of 2, you have a homomorphism back to integers because you're dealing with an infinite set.
That's actually a really good point. Yeah. Yeah, I think that's right. And actually, yeah, that actually comes up later.
Oh, okay.
Yeah, no, something very similar to that comes up. So we'll see if that's actually the same idea. Okay. All right. So yeah, I note that the prime ideal R over R. Sorry, the prime ideal over R of R is also a slice category, like this. Okay, so I wanted to know if I could get the properties for a prime ideal just from the fact that P is a ring homomorphism R to Z. So I looked around and I couldn't really find a proof, but most texts take this for granted, that the prime ideals are exactly the kernels of homomorphisms of R into integral domains, right? So if you take a homomorphism into Z, for some, if you have some ring R and you take a homomorphism of it into the integers, then its kernel is all of the whole set of R's for which that homomorphism is 0. Right? So it's all R's for which H of R is 0. And most texts take this for granted, that for any given ring, if it really is a homomorphism into the integers, then the subsets of R for which H of R is 0 are exactly the prime ideals. Yeah, the set of R and R such that H of R equals 0. But note that this is not true for all prime ideals. Okay, so it's not exactly the prime ideals. All right, so the sketches for the proof is, if you know the first isomorphism theorem on rings, and together with the fact that I is a prime ideal of R, precisely when R over I is an integral domain. So then the sketch goes on to say that what the isomorphism theorem is going to tell us is that the kernel of H from R to the integers is isomorphic to the slice category of R over the integers. Right, so that was a bit of a detour into ring theory. Okay, so now back to Awodey. He talks about arrows from terminal objects. So we talked about arrows into initial objects. Now we talk about arrows from terminal objects. So in Hask and other categories like that, we can pick out elements of a type. We can pick out the elements of a type P as arrows of type unit P. Makes sense, right? So these two things are isomorphic. So there's one such global element for each value of P. So, given a value of P, we can construct a unit to P and vice versa. We consider two arrows equal if they agree on points. That is, F and G are equal if for all points A, from unit to A, F composed with A is G composed with A. So then F and G are equal if composed with, if applied to the result of this, single element function A, we get the same. But this is not always the case. This is true in set and Hask. But if we consider the category of monoids, how many monoid homomorphisms from 1 to m? Remember, 1 is the single element monoid, so it's the unit monoid that only has a unit in it, right? So for a given monoid m, how many homomorphisms from unit to m are there? Well, there's exactly one. It picks out the mempty of the monoid. So how many does a Boolean algebra have? It has exactly 2. So we can go from the terminal Boolean algebra to a given other Boolean algebra in exactly 2 ways. We can either pick out the 0 or we can pick out the 1. Right. So that function to be a Boolean algebra homomorphism, it has to take the unit to either 0 or to 1. Okay, so instead of considering unit to A as our elements of our set A, we consider what's called generalized elements. Generalized elements X of type X to A. In CS, what did I mean by CS here? Computer science. Yeah, so we think of 1 to A as being closed terms, so terms of type A, and X to A as being open terms, that is lambda of some X returning an A with a whole of type X in it. Right, so they're open terms with variables. Then take example 212. So in any category C and for any arrows F and G from C to D, we always have F equals G if for all X, generalized elements X of type X to C, it holds that F compose X is G compose X. So why? It's easy to reason about this using a diagram. So if we have 2 arrows F and G, like that, and then we have a generalized element, which is an arrow X that goes into the domain of both G and F. So if we know that f of x equals g of x, then we know that the diagram commutes. If all we know is that, we know it commutes because that's what this diagram says. It says that f of x equals g of x, right? If we know only that f equals g, then these 2 branches are actually one arrow. Right, they're the same. And so this is really just a straight diagram. It's a straight line. And we know that a straight line commutes, and And so this is the same. So basically, if two arrows agree on elements, then they also agree on generalized elements. So generalized elements, what was this? Example 213, generalized element to test the non-isomorphism of two posets. Let me go back to the book. 213, okay, generalized elements can be used to reveal more structure than do the constant elements. For example, consider the following posets, X and A. So he has two posets. One of them contains X and Y and Z, where X is less than Y and less or equal to Y, and X is less than or equal to Z. And then A, the set A, which has A, B, and C, which are in in order. A is less than or equal to B, is less than or equal to C. Right? So that's on page 37. Right. So if we compare that on one element, that is on just the elements X, Y, Z, and A, B, C, that's not going to get us to whether these two are equal or different, right? Because it will actually forget the poset relationship. But if we compare on two elements, right? So what are all the two elements of X? So those are now homomorphisms from the poset 2 to X, right? So the category 2 considered as a poset, and then if we take a functor from that into X considered as a poset, then we get the following elements. So we get X is less than or equal to Y, Y is less than or equal to Y, this is the identity. We get the identity on Z, we get the the relationship between X and Y, and we get X and Z for this line 140. Let's define X. And then for the set A, we get 5 two elements. Right? We get the identity on A, identity on B, identity on C, and then we get AB, AC, and BC. Right? So, oh, sorry, it's the other way around. So there are 5 elements in X and 6 two elements in A. So yeah, we have a functor, which is looks like this, x2 whatever. So in this case, I'm taking this to be bool. So bool to something is the functor here, and under that functor there are these elements. So we can compare these two posets. If we compare them on elements, we're going to get the wrong results. If we compare them on two elements, we're going to see immediately that they don't have the same number of two elements. So great. Right. So here he's considering 2, or the Boolean set, to be the test objects. So that we're testing with. All right, page 38. Example 214. Okay, in the foregoing example, it is often the case that generalized elements based at certain objects are especially revealing. So elements T from T to A. So if you pick a particular T, it's especially revealing. So we can think of such elements geometrically as figures of shape T in A. Just as an arrow from 2 to P in posets is a figure of shape P less than or equal to P prime in P. As we have already seen. We have seen here that figures of shape 2 or shape Boolean in this set X are these elements, and in A are these elements. Oh, yes. So the arrows from the terminal monoid are entirely uninformative in the category of monoids. But those from the free monoid on one generator suffice to distinguish homomorphisms. So we saw that, you know, when he was asking, consider the category of monoids, how many monoid homomorphisms from the initial monoid to M are there? Sorry, from the terminal monoid are there for a given monoid? Well, exactly one, right? But if we consider the initial monoid, the free monoid on one generator, which is the same as the integers, no, the natural numbers, sorry. So that suffices to distinguish homomorphisms in the sense that two homomorphisms, f and g from m to m prime, are equal if their composites with all such arrows are equal. So we know that so the free monoid on one generator is the natural numbers. And we can think of generalized elements from the list of units to m as figures of shape list of unit in M. Okay. So let's see what I get with these notes here. Right, so the monoid homomorphisms from unit to M for a given monoid can't distinguish between homomorphisms. There's always exactly one figure of shape unit in every monoid. That's the mempty. So of course, f of z equals g of z only tells us that f and g agree on mempty. Doesn't tell us that f and g agree on any of the other elements. But homomorphisms from list of unit, which is the natural numbers, suffices to distinguish between monoid homomorphisms, and these arrows are of the form fold map f, right, where f is of type unit to m. So if two monoid homomorphism h and g agree such that g composed with fold map f equals h composed with fold map f for all f of type unit to m, then h is equal to g. Why? Well, because fold map f x's, remember that fold map fold map a to b, list of a to b for a monoid b. So it maps all of the elements of the list into a given monoid b and then sums them all together with the mempty being the base case. Right, so yeah, so fold map f of some list x's will either have the form mempty of type m if x is empty, or we'll have the form f of unit plus f of unit plus f of unit plus f of unit, etc. So it's some multiple of the element under f. So it's exactly, Jakob, what you were saying earlier. It's some you know, multiple of single elements, right? So I guess is now then isomorphic to the natural numbers, right? Or it's a homomorphism. It's a homomorphism from the natural numbers. And actually, that's what this is saying. So list of unit is isomorphic to the natural numbers. So this is a homomorphism from the natural numbers into this monoid. Okay, so if x is non-empty, then we're going to have this kind of structure. And then each such expression is a figure of shape nat, right? So it has the shape of the natural numbers in the monoid M. And then if we remember the universal mapping property for the free monoid, then for every unit to M on sets, there is a unique monoid homomorphism from list of unit to M on monoids. So in other words, the set M and the set of monoid homomorphisms from natural numbers to M are isomorphic. So this is the type under fold map, really. So for every monoid M, we have a figure of shape nat in it for every value M. And that figure is the set of all the powers of M, or all multiples of M, sorry. I say powers here in the sense that if this is the multiplication I should say multiples. So really what this is saying is that two monad homomorphisms H and G from M to M prime are equal if they agree on all the elements of the underlying set M. Make sense? So it's not a coincidence that the NAC monoid is the initial object in the category of list algebras. There is a unique arrow from it to every other list algebra, which are the other monoids, so it uniquely determines them. Yeah, so all of this really just follows from the freeness of the list. Cool, and we're at time, and I've gone through all of my notes. Awesome. Anybody else have anything? Nick, Yakov?
No, this explains it way better than Awodey does, though.
Great. I guess I'm really just adding because like I read the chapter. I didn't understand anything. Sat down, thought about it for a couple of hours, wrote down these notes. And so I'm really just adding clarifications for like stuff that helped me think about it.
Yeah.
Yeah, I don't know enough ring theory to tell you what that offhand comment, or to prove that that offhand comment he makes on the bottom of page 35 is actually true. But all right, cool. So next time we'll go over products, and I will encourage you to both read the. So I'm thinking it's not going to be next week because like a lot of people are out, right? And we're sort of getting rid of all standing meetings next week. So I think what we'll do is we'll meet in the new year, and in the new year we'll have read products in Awodey. And I also want to encourage you to read Bartosz's chapter on products and coproducts, because those two things I think complement each other really well.
You need a minute or?
Sounds good.
Give me a minute.
All right.
Well, thank you, Renar.
Thank you guys. Later.